Hello, YouTube community. This is John Harmon, your Atom Advisor, coming to you to talk about disseminating information on fusion developments. This is another exceptional company up in Washington, Zap Energy. I'm going to share with you what their concept is. They're developing a device that's going to help with fusion power. It's modular and scalable. Basically, climate change. There's deniers, but we all know the weather is changing. There is something to all this greenhouse gases. We need to get to really clean air production, and we can get there. So we urgently need safe, reliable, zero carbon energy without the waste. That's the beauty with nuclear fusion. Nuclear fusion is actually better than nuclear fission. Jump ahead here into their device. So Zap Energy's got this modular device. Let me step you through it here. They're using this, called Z-pinch. So they take some gas and inject it in the top, and they're using the deuterium and tritium gas, hydrogen isotopes. Then they're inputting the current. Then you see the plasma. Down here, they're driving the current through the flow to create a confining field, compressing the plasma. The compression is what results in the fusion. Then the resultant neutron burst is actually captured by the liquid metal within this device. So the higher the current, the greater the pressure, temperature, and density of the plasma. So their unit is going to be compact, economical, going to be tolerant. It's going to be able to take the high energy from the neutrons. The beauty of this design is it could actually be deployed more in a microgrid setup to provide power in different remote locations or cities. Also, with all the data farms, the IT infrastructure around the globe, our banking, social media, communications, we're all connected in society, and it takes a lot of energy. So here's some more footage of their devices. They're modular. They can deliver small communities, scale to meet the demand of large cities. It's really going to be a pretty cool technology they're working through right now. They just received a DOE grant, $5 million. So it's an inevitable future. There's so many companies right now working on and building towards it. I'm going to go ahead and jump into Ben Levitt, their R&D VP. Let's hear from Ben.
What's critical right now, and why I'm working at this and why so many of my colleagues are working at this, is because of climate change. Of course, we would love to have an abundant source of energy, which thermonuclear fusion provides, but really it's the carbon-free aspect which is so critical. We see on the news, every day forest fires, flooding, more intense storms, and it's really here. Climate change is here. So people talk about the energy transition, but we don't need it in 2040, 2050. We need it now. Thermonuclear fusion provides such an abundant source of energy, with the fuel being parts of seawater. There's no other thing that compare to this. It's really a one-size-fits-all solution where all other parts of the solution become optional once you have thermonuclear fusion. To explain the difference between fission and fusion is important, and we have a lot of outreach and education that we need to do in the industry to make sure that the public knows and is aware of this difference. They're really opposites. Aside from the word nuclear, they don't have much in common. As I said, fusion is combining light elements into heavier elements, while fission is the opposite. You're taking very heavy elements like plutonium, uranium, and you're splitting them. Both of these give off energy. Fusion gives off much more energy, about 4 times more energy per mass of the fuel. However, there's a bunch of things that it also does not do. It is not radioactive to nearly the same degree that fission is. The fission process, the reactants from the fission process can be radioactive for tens of thousands of years. Whereas fusion, some methods have no radioactivity, and some have very little radioactivity, where you have a problem on the scale of a few decades. The end user won't notice a difference at all, right? This would just be a different way of getting power to the grid, similar to power plants that already exist, to a coal-fired power plant or a fission reactor. technology would appear on the grid and you would use it. So you don't have to change your AC outlets or anything like that. But you would have the knowledge that this is 100% carbon free, and it would be abundant and it would be on demand. So this has certainly the Z-pinch technology that we have, since it's modular and it's a pulsed machine, it can follow demand. It can turn on and off at will. In terms of where it could be, the safety allows it to be anywhere. You could have a small modular 200 megawatt plant, which would be, the size of a few car garages, for example, that would power Everett, Washington. You could have a 50 megawatt plant, which could be on the basement of a skyscraper in the middle of Seattle. Or you could have, since this is modular, you could have something more akin to a 2 gigawatt large fission power plant on the outskirts of the metropolis, powering the entire metropolis.
Now let's go to one of the research engineer, Hannah Meek, hear what she's got to share.
As a woman in engineering or in science, I was always just like, I want to enter a field that contributes to humanity in a much bigger way. And for a while there, that was like space travel. And I was like, I don't know if that's really contributing like right now. And this right now is like, I feel good about what I'm contributing. I'm not using my degrees for weapon development. I'm not using my degrees to help an oil company. I'm using my knowledge and my skills to try to get the Earth to a better spot. Climate change, and we're running out of sources here where it's just, I can apply myself to this and see change immediately, and try to see this through to where you do flick on your lights and that came from us. That'd be great.
Now let's hear from Morgan Quinley.
I'm Morgan Quinley. I'm a senior research engineer here at Zap Energy. I've been here for about 1.5 years. I think I was employee number 6. And what I'm doing here at Zap now is sort of leading the development of our next generation fusion experiment, sort of the next step in performance beyond what you see behind me. I'm sort of working on the experiment that will hopefully get us to Q equals 1, or scientific break-even, where we get more energy out in the form of neutrons than we put in from our big capacitor banks. Core bit of the experiment on a given shot, because we fire this experiment, it doesn't just run continuously. We fire a shot, wait a little while, and fire again. The core bit is that we charge up these big capacitor banks and store a lot of electrical energy to many thousands of volts. When that's done and ready to go, we very quickly puff in gas into our vacuum chamber here. The gas enters in between our electrodes. We close some switches to apply those many thousands of volts across that gas, and hopefully that breaks down the gas and creates sort of, a plasma between them, roughly like a lightning strike. And then what happens is we ideally form this nice uniform plasma between our 2 electrodes, and the magnetic pressure kind of squeezes the plasma downstream, like you were squeezing a tube of toothpaste almost, pushing it downstream. And then by the geometry of our electrodes, this special geometry, when it reaches a certain point, it's pushed further into a very long, skinny column of plasma, which we call a Z-pinch. So it's a column of plasma along the Z-axis of our machine. We continue to dump in more and more and more energy to compress that plasma further and further and further, making it hotter and hotter and higher pressure, causing more and more fusion reactions to occur. And those fusion reactions kick out neutrons, which we measure with our detectors. Right now, those neutrons just go into the walls of our lab and bounce around until they, land in some drywall or something like that. Eventually, this entire device will be surrounded by liquid lead and liquid lithium, which are great neutron absorbers and neutron multipliers. And so essentially what they will do is the neutrons will fly out into this blanket of lead and lithium, bounce around many, many times until eventually they've given all of their energy to the lead in the form of heat. And when that lead is nice and hot, we can direct that heat through a steam turbine to generate electricity and drive it onto the grid. Technology that can come in and be used anywhere in the world, any time of day, under any weather conditions, and provide reliable power output while not polluting your air and streams and land. So I think it's hugely important for that reason. Yeah. The grand goal is to achieve engineering break even and then move into a fusion reactor. So basically to turn this experiment into a nuclear reactor that can be used anywhere in the world to provide energy with no inputs other than a couple of isotopes of hydrogen. That's it. And the outputs being only helium. Yeah, that's the grand goal, a clean source of abundantly available energy.
All right, let's hear from their chief engineer, Brian Nelson, their chief technology officer. All right, Brian.
I'm Brian Nelson. I'm the CTO of Zap Energy. And our concept, which is called the Sheared Flow Stabilized Z-Pinch, and I'll just call it Z-Pinch for simplicity, we simply drive a current through ionized gas called a plasma. And as you drive that current higher and higher, it makes its own magnetic field that crushes it down and gets them to temperatures that can allow fusion reactions. Now, to get to where you get more fusion energy out than what you put in, we have to get across a barrier called Q equal 1, where Q, it's the ratio of power out over power in. And of course, if you can't get to that, you don't have a fusion power plant. So for us, it's increasing this current. And behind me are power supplies that can produce this current, and we're getting up to within about 75% of the current that we think we need to get to for Q equal 1. And then from there, to go to a reactor, a full fusion power plant would be about twice that. It is very difficult to do outside of the sun has a huge advantage of its gigantic mass, as that's how they can crush the particles close together. And if you get to high enough velocities, they can touch and undergo this fusion reaction. And it's very cheap. I calculated that the average house, which is about 12,000 kilowatt hours per year, the cost of the actual fusion fuel itself is about $2.
All right, team, what do you guys think? I'm excited to see what they're doing here. I believe this device is really going to have a lot of potential. Encouraging my praying type friends to let's pray these guys and solve the technical challenges they need to overcome to manage the neutrons, to capture the heat, to integrate the steam plant. They're able to do this all safely and economically and reliably. And I'm really excited to see what they're doing. So, hey, if you like what you're seeing with the channel, you know the routine. If you're a YouTuber, hit the subscribe to the channel, hit the like. It helps get this information out to the greater community. Put this together just because I've got a lot of information and I'm just looking to share it and make more people more aware and, give people some hope. With that said, peace out.